pero tendríamos que ir comenzando. El primer orador de la mañana, 2 años. Y me dejé el telescopio en Canarias. Eh, Föster, ¿cómo es tu nombre? Perdón. Francisco Föster, y nos va a hablar de The ALeRCE Astronomical Alert Broker.
Okay. Gracias. Perfecto. Gracias. Perdón, ¿y son 10 de preguntas o? Ah, perfecto. Gracias. Ok, bueno, primero agradecer a todos los que llegaron hoy día después de la increíble escena de ayer. Y gracias a los organizadores por esta increíble conferencia. Difícil organizar algo de este tamaño, así que felicitaciones y muchas gracias. Okay, so I will switch to English and I will talk about the ALeRCE broker. ALeRCE is one of the 7 community brokers selected for the Vera Rubin Observatory, and it's an initiative that is started in Chile with few institutions, Center for Mathematical Modeling, the Millennium Institute of Astrophysics, Data Observatory, and Universidad de Concepción. It's really an interdisciplinary project with people from astronomy, computer science, mathematics, statistics, etc. So what is the motivation of ALeRCE? Well, it's a new generation of large ETENDU telescopes. So these are survey telescopes. And ETENDU is a product of the field of view and the collecting area of a telescope. So this gives you an idea of the volume that you can explore in one shot. So in this plot, you can see that the circle size is the ETENDU, and the Vera Rubin Observatory, with its legacy survey of space and time, LSST, is really dominating. And today you have surveys like Zwicky Transient Facility, Atlas, well, Subaru, etc. So the motivation to build ALeRCE was the arrival of LSST in Chile, and that will start in 2025. And you can see that the camera has 3 billion pixels with almost 10 square degrees. And this is a comparison between different cameras. But this is in an 8-meter class telescope. So this is a picture of the construction during the eclipse in 2019, and now it's almost ready. Okay, so some key numbers. The camera has 3 billion pixels, as I said. The typical cadence will be 3 nights. Will operate for at least 10 years, and it will observe about 40 billion objects. So it will be like a really rich data set of very deep and also rich in time domain. So with at least 800 observations per point in the sky. And with every observation, the telescope will detect changes in the sky, and this will generate an alert stream. So reporting everything that changes during the night. And with every observation, you will get about 7,000 variable stars, around 3,000 solar system objects, around 200 supernova, 770 AGN, and not more than 500 bogus, things that are not real. So alerts consist of this kind of image stamps centered in the position of the object, and you will get around 10 million per night. So it's impossible to filter this by hand. You need the help of automatic tools and artificial intelligence to really filter and make sense of what's going on and what to follow up. So the future time domain ecosystem will look something like this. You have survey telescopes that will scan the sky from the ground, from the space, in different wavelengths and messengers, and they will serve an ecosystem of brokers. These are the 7 selected community brokers for Rubin, and they will feed downstream brokers, so brokers of brokers. So this is a new kind of world, and they will connect to follow up telescopes to know what to follow up, and also just with the wider user community to do real-time analysis or post-processing and systematic analysis of the type of astrophysical object. So the call for community brokers was in 2019, the letters of intent, sorry, in 2019. The call for full proposals 2020, and the selection was made in 2021. As you can see, it's very top-heavy distribution, 6 brokers in the north, and only 1 in the southern hemisphere, and it's ALeRCE. So ALeRCE started in Chile, but we will be really happy if this becomes more Latin American broker. So what does the broker do? Well, at the beginning, it was not very clear. It was just you ingest the stream, and then classify or filter. But as brokers have started operating, we are really kind of creating what the broker is. And these are some of the services. You receive streams of data using Kafka is a tool. You cross-match the alerts. You provide access through databases, APIs. You filter the stream. You classify. You provide characterization, features, watch list. So if you have a list of coordinates in the sky, you get alerts of when something's going on in this part of the sky. Connect with follow-up telescopes. Do multi-messenger or multi-stream outliers, regular data releases, and make everything reproducible. So alerts consist, as I said, in image stamps. So a sequence of image stamps as you get more and more alerts from a given position in the sky. In this case, it's a supernova. And the associated multi-band time series, so the light curves. And this is the input that ALeRCE uses and other brokers use to filter and classify. So the ALeRCE broker is the automatic learning for the rapid classification of events. That's the acronym, but it's also, as you may know, it's a tree from the south of Chile and Argentina, and is currently estimated to be the oldest tree in the world, about almost 5,500 years. So what are the scientific questions that we want to answer? We care about transients, variable stars, AGN, solar system objects. And we have astronomers working in all of these areas. And I can tell you that we don't have enough astronomers. We're so busy making ALeRCE work that we need to have more use cases and users that can tell us where to continue doing the development. So the team is composed of, well, at the moment, we're 2 PIs, myself and Guillermo Cabrera, a scientific board of 8 researchers, and a strategic board of the funding institutions, that I mentioned before. And the way we operate is with 3 teams: the software engineering team, machine learning team, and astronomy team. And we work with agile methodologies that are brought from the industry. So you iteratively work over something. You start with very simple solution, and then you iteratively improve it. And something we have learned is that to go from the idea to the paper takes a long effort, a lot of effort. But to go from paper to have this in production is much harder. So for this, you really need software engineers. And so currently we have 6 full-time engineers and 2 postdocs. The postdocs are astronomers, and the engineers are machine learning and software engineer experts. And we are moving into separating the teams into smaller teams, focus on science cases, so scientific questions that you want to answer, and then develop the tools around these questions. This is very important, not to get lost in all the possible things that you can do. So the lead engineer is Diego Rodriguez, and also we have admin teams from the host institutions is very important. So in terms of publications, we have so far 17 accepted papers. You see all the statistics, but really what we really are interested is the mentions, so people that are using ALeRCE, and you see that this is growing very fast. 144 articles mention ALeRCE, they use it, and we also found one paper that actually they say, we try all the brokers and we use ALeRCE because it's the easiest, is rapid and complete databases, informative website, connections to external archives, etc. So, and we don't know these people. So what is the road to LSST? LSST is our goal. In 2019, we started ingesting alerts from the Swift Transient Facility in the US, the CTF, with about 300,000 alerts per night. 2022, we added the ATLAS telescopes. It's a network in Hawaii, South Africa, and Chile. And this is about 1 million alerts per night. 2022, 2023, this year, we started participating in classification challenges using simulated LSST data, the Elastic Challenge. And 2024, we will get the first commissioning data. And maybe we can also ingest data from the La Silla-Schmidt Survey Telescope, LS4, that is kind of follow-up survey telescope, trying to do similar strategy than LSST. And 2025, start of full operations. So now I'll discuss use cases. And all my talk will be focused on use cases. So for example, if we get an alert, can we classify it really, really fast just with the first alert and not waiting for the light curve? Yes, we can. And the way to do this is to use just the image stamp. It's the most informative part of the alert when you have only one alert. And so use a convolutional neural network to classify into a simple taxonomy, AGN, supernova, variable star, asteroid, and Bobus. And it works surprisingly well. And this allows us to develop a tool called the Supernova Hunter, where every morning you get the latest supernova and you visually inspect about 100, and of these 100, maybe 20 are submitted to the transient name server. So this means that a lot of people are using ALeRCE. This plot is not up to date, but when the last time we counted, we had users from almost 130 countries. This was really not expected for us. And today, we are the third largest reporter of transients to the TNS, and also of things that are classified as supernova. And actually, of all this group of groups that report transients, we provide the purest sample. So, but one thing is to classify just with the image. But what about the host galaxy? If you have an extragalactic transient, the host galaxy is very important, but you need to automatically identify it. So for this, we develop a tool that is inspired on the animal vision that has multi-resolution images of a center around the transient candidate, and that automatically can tell you which one is the galaxy. And this uses also convolutional neural networks, and is free to use with pip install AstroDelight. And first we were saying, okay, we will do the CNN convolutional neural network to solve this problem, to see whether it works. But and if it works, it will be faster than other methods. But it turned out that it was not only faster, but also more accurate and more robust. So is Delight, compared to all different methods, is the one with fewer errors in both the position and in the redshift that you get after doing the association. So now we are using Delight to automatically associate the host galaxy, and when we report supernova, we automatically select the galaxy and include it in the report. So when you go to TNS, you will see the most likely redshift and so on. So what about doing the same but with LSST? Because this was with CTF. Well, yes, we can do that, but there is a problem. The image stamps in LSST are tiny compared to CTF. This is the size of an image stamp in CTF, and this is the size of an image stamp in LSST. So when you have things like glints, satellite glints, like in this case, you can be fooled that this is a supernova when this really is a satellite. So for this, we're developing multi-resolution representation of the image stamps as well, and we're proposing this to LSST to modify the stream. And we published this recently, showing that is for the same number of bits, you can do much better classification. So can we classify the light curves now using relatively complex taxonomy? Well, our attempt, what is in production today, is the following taxonomy. So this is probably not refined enough for all the science cases, but it's the first classification where you can start doing your more refined classification. So we have 3 branches: transient, stochastic, periodic, and different subclasses within each branch. And we are now expanding the transient branch to include tidal disruption events and microlensing events. Tidal disruption events will be very important in LSST era because we will finally get a reasonable size sample. So we also provide features. We compute around 880 features for every object. And so here you can see the top features for each of the classifiers in this hierarchical classifier that we use. And basically, well, makes sense. For periodic objects, the period is most important. For transient, it's the shape of the light curve. And stochastic is wise colors turn out to be very important. So this is the light curve classifier, and this is the confusion matrix. So these are the true label versus the predicted label, and you can see the 3 branches of the classifier and how we perform. So with this information, we create a web interface, which is the ALeRCE Explorer. Yes. So here you can quickly query objects, for example, type 2 supernova. You get a list. You can explore some meta information, so probabilities, machine learning probabilities. You can see the image stamps. You can see the light curve context, cross-match information. And it's kind of becoming the standard for many people. When they select supernova, then they go to ALeRCE website to look at it. We spend a lot of time developing this tool and making it very user-friendly. So what about the past evolution? Because this only provides information about the alerts when the object changes significantly before compared to some reference image. Well, CDF also provides the data releases. Oops. Well, you cannot see, but the red and green points are the alerts, and the light blue and gray are the data release. So if you didn't have this information, you have no idea what this object is really doing. And this object was identified as an outlier event because we had access to the data release information. So this is also very important. And in fact, we have published some papers on outlier detection. Some people think that this will be the biggest discovery from LSST will come from outliers. So we are trying to tackle this problem as well. And you can detect outlier events and outlier phases for a given event. So we are doing this in these 2 papers. So what about improving the cadence if we combine different telescopes? Because ATLAS observes with a faster cadence, for example, than CDF. So we are doing a multi-stream processing of the alerts. So we have the CDF stream, and we put a machine in Hawaii to produce a test stream from ATLAS. And so we archive these alerts, and we cross-match, and we have something called the sorting hat that tells you whether the object is the same. So if it's the same, you can get a combined light curve and basically improve your classifier based on these 2 sources of information in real time. So also, because of this, we have learned many things about databases. We started using, and we're currently using Postgres as a database engine, but we realized that for LSST era and actually ATLAS, we need to move to non-relational databases. So we're at this stage using MongoDB now with CDF, ATLAS, and Elastic. And we think that we will continue using MongoDB for Ruin. And we have had to develop new tools to interact with the database in real time with a stream. So we call Scribe. And so you see that there's developments that come from astronomy that can impact other areas as well. So what about physical parameter inference? This is what we really care. We care about the physical nature of the objects. So this is an example of a light curve that combines CDF and ATLAS data. And you can see the inferred physical parameters using MCMC. And in fact, we can not only get the supernova, in this case, physical parameters, but we also can get the distance quite accurately, much more accurate than using, for example, photometric redshift from the galaxy. So this could be like a light curve photometric redshift. So can we do this in real time? Yeah, for this, we're using something called amortized variational inference. So in this case, you have a neural network that can predict the parameters of the posterior distribution. So you can do this very fast, and you can get posteriors for thousands of objects in 1 minute. So this is required to scale up to LSST. So what about attention-based models. So you may have heard that in the machine learning community, there is something called attention and transformers that is really changing everything. One example is ChatGPT. So all these large language models use attention. And this started in the natural language processing community. So we adapted some of these tools for astronomy. So this is the typical use. So translation. So we have el perro café se puso feliz y me ladró. So you can say the brown dog got happy and barked at me. So you see that there are some connections between words. So each word has to pay attention to a different word in the translation. And in this way, the algorithm can translate. And so far, before transformers and attention, neural networks had some memory that was fading away gradually. With transformers, they have perfect memory up to some point. So this is the difference. So when you hear ChatGPT with a context window of 132 kilobytes, this is the window of memory. And they can remember exactly everything up to that point and nothing before. So, but this kind of size of context window is perfect for LSST because the light curves are not very long. 1,000 point is not very long. So basically, you get an attention score for every word. And we tried this in a paper by Oscar Pimentel, 2023. And after many years trying, making compete the classic machine learning algorithms like random forests with more modern methods like recurrent neural networks, and failing to beat the classic, with transformers, we actually are performing better. So this was the first time that we beat the random forest. So the green line is the transformer. And this was in Universidad de Chile and Universidad de Concepción in the south of Chile. A parallel work the same year also applied transformers to light curves in astronomy. And they're aiming to build a foundational model. So something like you train for all the data that you find, and then without any previous information, you try a new telescope and it works. So this is by Cristóbal Donoso Oliva. So this is an example of what the Oscar work is doing. So you have the light curve, and you can see the size of the dot is the attention that the model is paying to each individual point. So for example, in type 1a supernova, you have a secondary maximum in the R band, and it kind of pays more attention to this point. And yes, it works really well. So what about doing the same for LSST? So LSST is not just 2 bands like in ZTF, it's 6 bands. And the cadence is not as good in one given band. So you have 15 days typical cadence per band and 3 days typical cadence between all bands. So for this, we entered the Elastic Challenge. This is the calendar for the first part in 2022. And this is 2023. Just a few weeks ago, the second part of Elastic started. And so in the first part, we did really well. We had, well, it's kind of not public information, but I can tell you that we had the best models. And this is the confusion matrix. And we call this model ATAT, the astronomical transformer for time series and tabular data. So we mix the time series and all the tabular data that you have, like redshift, maybe features also from the light curve, and so on. And this is led by student Nicolás Astorga and Guillermo Cabrera in Concepción. And by the way, Nicolás is now doing a PhD in medical data. Rodrigo Carrasco, that did the convolutional neural network for ALeRCE, is also doing a PhD in medical data and machine learning. So we're transferring to other areas. And what about notifications? So let's say I have a list of objects, my favorite objects, and I want to get notifications. Every time there is an alert triggered around this position of the sky, this is called the watch list, a watch list. This was first developed by other brokers, but we also have one. So you provide a list and just upload a CSV file, very simple, and you get notifications. And this object is connected to the ALeRCE Explorer. So this is the light curve of the object, and you can get notifications by different means with different rates. So how can you access all these products? This all is free to use. Everyone can access. There's no charge, nothing. And we are really happy if you use it. So we have APIs. So API is a way to automatically interact with the database. Something that is going to be key in the future for all these tools to work well is the interoperability. So to make everything interoperable. So APIs can allow you to do quick queries to the database. We have one for the stream and also for the data releases of CDF. And we also have a Python client, pip install ALeRCE, that allows you to also do even easier interaction with the database. But we know that astronomers have complicated use cases, so we can also provide, for the more expert users, direct access to the database. So if you know SQL, you can directly query using a Jupyter notebook. So it's very simple. So the living database that is being populated every day is in Postgres. We have one in Mongo, as that I mentioned, that is in staging. That means it's not public yet. And these are some of the numbers, many objects that we have classified. And basically, it's organized in like things that are independent of time and the band, things that are independent of the time but depend on the band, and things that depend on the time. So these are the largest. Sorry, the other way around. So this is the light curves, and this is the largest table. So can we train young scientists to use ALeRCE? So we spend a lot of time developing Jupyter notebooks centered in the different use cases. And you can see some example here centered on supernova. So really, I recommend you to visit our GitHub and start playing around and let us know if you find anything, you want to improve something, we want to know. So what about if you don't know a lot of SQL and you still want to use the advanced connection to the database? So something I can tell you now is that we're playing with large language models. And this is an example. In natural language, I tell ALeRCE, please return the object identifiers, most likely class, probability, blah, 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 of objects classified as this class is a supernova, according to the light curve classifier with probability larger than 0.6. And this returns the SQL query that was used to generate this plot of light curves. So I think this is the future. The future will be really natural language interaction with everything. There's also, we found out that it was a recent tool developed for Gaia, Chat Gaia, that is doing something very similar to what we're doing now. This is still not public. And actually, I told ChatGPT, can you tell me can you explain this figure? And actually, it works really well. So it's a stylized sun with rays extending, map of South America, the text, the dates, and tells you everything. So apart from text, what is coming is a multimodal approach of large language models. So they will receive text, images, spectra, everything that you have. And the challenge is going to make these models learn how to interpret all of this combined data, which is the way we make decisions about the data. So I think I went a bit fast. So the next steps and challenges in terms of infrastructure, we are moving to multi-stream. Well, we're already multi-stream. We are moving to NoSQL database. We are scaling up to Rubin. This is really challenging. It's much harder than it sounds. And for this, we're moving into hybrid infrastructure. So I didn't tell you that we are operating in the cloud, in Amazon Web Services. But we know that the cost in the LSST era is going to be impossible to find. So we are doing hybrid infrastructure. So the pipeline runs locally, and all the services are in the cloud. That's our strategy. In terms of machine learning, we are building new multi-stream classifiers. We are doing forecasting, outlier detection, inference in real time. So this 0-1 of few-shot learning means I have a model that has never seen data from a given telescope, and I want to classify. So with no information, with one example, with a few examples, and so on. And I think the biggest challenge is doing the multimodal models. So things that can ingest and make sense of different kinds of data, and including lateral language processing. So in terms of astronomy, identifying the new use cases, adapt to the new science that is going to happen with LSST, and train astronomers to this new way of working, actively participate in the science collaborations of LSST, yeah, and kind of maintain the position that ALeRCE has developed, becoming one of the most relevant brokers today. So I really encourage you, if you're interested in this work, if you want to collaborate, write to us, and we would love to make this not just a Chilean broker, but Latin American broker. So this is the webpage. So we are really, as I told you, exploring many use cases. We need interoperable brokers to prepare for LSST. And if you want to join, especially if you think you can fund an engineer, let us know. We want more partners in this endeavor. So I think I finished much ahead in time. And the last thing I want to mention is that in 2 weeks, we're organizing a conference. Maybe it's too late, but if you're interested to come, let me know. Maybe you can make some space. And it's going to be centered around these streams of data. It's called Unveiling the Dynamic Universe, Cosmic Streams in Data Proving in Puerto Varas in the south of Chile. Yes, and we will do 1 day hot springs. So yeah, so I finished much ahead in time. So thank you.
Ok, tenemos tiempo para unas cuantas preguntas. Vamos a empezar por los visitantes luego.
Hi, thanks for your talk.
No.
I have 2 questions. The first one is, I understand that the different brokers may have same goals, same scientific cases. And for me, as a user, it's unclear which one should I choose.
Yes.
So my question is, what makes ALeRCE unique, or what can I do in ALeRCE that I can't do in the other brokers, or I can't do that well?
Yeah.
And the second question is about, is ALeRCE open source? And can you comment about transparency and things like that?
Yeah. Yeah, so for the first question, there are a few, well, it's a typical question that we get. It's like, why, I mean, what is the difference? It's, now we are kind of a Cambrian explosion. Everyone is doing different things, and eventually we will converge, I think. And maybe new alliances will start happening and so on. But some things that we do that no one else is doing is using the image stamps to classify. And this allows us to be the fastest classifying. And that's why we are on top of the list on the TNS. Some other things that we integrate the data releases of CDF. And we spend a lot of time on the web interfaces, other brokers too. A lot of features. We have more features, I think, than other brokers in terms of classification. And open source, yes, everything is open source in the GitHub of ALeRCE. And yeah, and I think it's something important is also like, at the beginning, when I started this project, I thought, okay, we will put an astronomer doing coding. Astronomers are very good coding, of course, but that's not true. You need software engineers. And we have a big team of software engineers, so they are very careful on the coding. So you have all the tests, unit tests done, and so, etc. It's all in the public repository. Yeah.
Gonzalo.
Sí, yo tenía un par de preguntas. Una referida a los bogus que mencionaste.
Ujú.
Haciendo un cálculo rápido, vi que más o menos del orden del, poco menos del 1%, pero creo que entre el medio y el 1% iban a ser clasificados, o serían clasificados como bogus. Digo, dado que muchas veces los nuevos temas, las nuevas preguntas que nos hacemos parten de cosas serendípitas, o sea, ¿qué es lo que se piensa o por qué pueden aparecer esos bogus?
Sí, bueno, en
Eso-
realidad, perdón.
No, esa sería la primera. Si querés responder esa, después la
Vale.
segunda tiene nada que ver con esto.
Sí, en realidad no es que se clasifiquen como bogus, sino que deberían ser clasificados porque son efectivamente bogus. Porque la pipeline no es perfecta y siempre se cuelan malas restas o cosas de ese estilo. Y las especificaciones del SST es que no pueden haber más de 500 bogus por observación. Pero efectivamente los outliers es lo que todo el mundo está pensando y es lo más interesante probablemente del SST. Y para hacerlo bien hay que tomar en cuenta toda la información. Por eso estos modelos multimodales son tan importantes. Porque a veces la curva de luz se ve normal, pero si tú miras la imagen te das cuenta que en realidad era basura. O si ves la imagen se ve bien, pero la curva de luz te muestra cosas raras, entonces hay un problema de calibración. No sé, el redshift se ve raro, entonces ese es el problema, yo creo, más importante. Cómo identificar las cosas que son novedosas. ¿Y la segunda pregunta?
No, y la segunda pregunta era, mi área de intereses son los objetos del sistema solar. ¿Qué es lo que se está trabajando en ALeRCE y qué gente está trabajando en ALeRCE en relación a temas de
Muy poca gente.
asteroides o cometas?
Muy poca gente. Teníamos un estudiante, José Peña, que desarrolló un código para obtener los parámetros orbitales y funcionaba perfecto, pero José, siendo tan bueno, se lo llevó a la industria. Y en este momento no hay nadie del grupo, probablemente hay gente afuera, no sabemos, que esté trabajando en sistema solar. Pero si están interesados, felices nosotros de entender cuáles son sus necesidades y si podemos desarrollar algo en conjunto. Incluso no es necesario ni siquiera preguntarnos, o sea, pueden llegar y mirar la base de datos y, y usarlo sin problema.
Francisco, trabajo, impressive work. I have a question because you mentioned the attention and the transformer way to classify these things. And I was wondering because you mentioned the gap in the stopping time that the algorithm is thinking.
Yeah.
I was wondering about these slow varying events, for example, in AGNs, if you are able to detect them, something that is varying very slowly, not like as
Yeah, I think that it is possible, and the size of the light course in LSST is really tiny compared to the number of bits that you can store in these context windows. So for us, it's not a problem. Maybe if you're doing audio classification, or maybe if you put all the images together and try to do, maybe you can start having problems with the context. But what we're seeing is that the context window is growing and growing with the latest version of the transformer and so on. So I think it's not a big problem for us. But also, for example, if in text, if you give ChatGPT a big PDF file, it will start forgetting at some point. So there are strategies to store information from the past, let's say, and access this in a more intelligent way. So we can apply eventually the same tools for astronomy.
I also had two questions. The first one is very simple. Do you have microlensing as one of the type of objects that you are trying to detect?
We are including, not now, but we are included in the next version of the classifier because many users have asked the same question. Yeah.
And the second one is, what is the role of the secondary brokers? So that I understand the primary brokers, the first line that you had are people who identify interesting objects. And are the secondary ones meant to alert the telescopes for follow-ups, or what is the role of the secondary?
Yeah, there are many roles. So let's see if I can move. Well, one thing is that you can do, if you care about a specific science case that is not included, like here. So let's say I work on supernova, which in my case, I work on supernova, and I know there are many subtypes of type 1a supernova. So this is not enough for me. So then I can build a more focus-oriented, like science-oriented classifier, starting from the point of ALeRCE, and I don't have to use all the billions of alerts from LSST. So I have a filter stream, for example, and then I subclassify this. So we can also provide this, like a kind of custom filter stream for certain users. And there are other brokers that do the follow-up, specialize on doing follow-up. So they connect to, they know how every telescope works. They know how to talk to the telescope. And so this is their strengths. And we will start populating this more and more. As I said, we're in kind of the Cambrian explosion now. So we're exploring all the parameters. Yeah.
Thank you, Francisco. That was great. Bit overwhelming, so much data and so much information.
Yes.
I was wondering, what will be the availability of the classification products? Like I'm thinking about the pulsating stars and things that aren't really rapid transients, given that LSST is proprietary data.
Good question. So everything from the stream of LSST is public. So the alert stream can be used by anyone. But the data releases, and if you want to access the images and do some post-processing, that's proprietary. So, but there are many things that you can do just with alerts, as we are doing now with CDF. So most of the classifiers only use the stream. That the stream means everything that moves 5 sigma with respect to some point. So if it happens, I mean, if you have let's say an eclipsing star, you will detect the eclipse.
So you will have the actual light curve available?
The light curve that is 5 sigma from the reference.
Okay.
Only the points that are 5 sigma from the reference.
Okay.
But if you have another catalog, you can go and see what was the reference. Okay, so and then you get the light curve.
Okay.
Yeah.
Thanks.
Yeah, but there are many things, restrictions on what we can do with the LSST data. In the specification says that we cannot provide any data that can be used to infer the original data. But that's impossible. For example, if I give you the absolute magnitude and you have the apparent magnitude, you know the redshift. Many things like this. So it's going to be a big question how to, what data we can provide. Yes.
Okay.
Yeah.
Thanks.
Preguntas, questions?
I have another regarding the classification, because, for example, you have the cases of binary stars, but for example, the CTF, I think, is not enough to resolve the binary objects or quadruple object like the AGNs, for example.
Mhm.
So you cannot use a secondary broker to find your objects if your objects are not that. For example, these quadruple lens AGNs are not going to be classified there.
Yeah, this is a very interesting case, and I think it's one of the most difficult. If it's like to connect alerts that are not especially coincident in real time in the stream. And for this, I think we need specialized sub-brokers. Or if you are interested, we can talk and maybe we can incorporate it into ALeRCE. But yes, we have heard the same question from other people, and maybe Caroline, I think they talk the other day, can tell more about this. Yeah.
Okay, I have one question. It's a more general one, right? You know that for surveys, it's not only the telescope, but also the observational strategy that affects a lot what we will discover.
Yes.
Right. And when I attend all these LSST talks, I feel like I'm in a deja vu on pan stars when I was a student long time ago.
Yeah.
longer than I want.
Yeah.
That one star will solve every problem in astrophysics, and then we know that this doesn't happen because you cannot have an observational strategy to solve everything. With your experience analyzing ALeRCE, ZEF, etc., what do you think that about the LSST observational strategy, the cadence, the exposure time, the filters? What are the objects that we will really be able to discover in an optimal way, and what are gonna be the subproducts?
Yeah, I
right?
think it's a good question because the strategy in LSST is not particularly good for time domain, and in the sense that the cadence maybe could be higher. There are the drilling fields that will have faster cadence, and perhaps the most interesting objects will come from this. But I think the strength of LSST is to really have large numbers of everything. And that means you will start discovering new subpopulations that perhaps you had not identified before. And new astrophysics in that way, so more statistical discoveries. The most interesting discoveries maybe will come also from the nearby universe, because you can do the spectroscopic follow-up. The 30-meter class telescope will have very small impact because, I mean, it's very expensive to observe. So I would say the most important thing is the numbers. This will be the biggest difference with other surveys. But it's true that you cannot solve everything with one strategy. And that's why it's important to include all the telescopes and all the information, everything you have.
Yeah, I always think that in this kind of survey, you have to have one strategy for one particular problem, and then the others should be somehow subproduct, but not because otherwise you do not do good things on anything.
Yeah, I mean, for example, a few years ago, we used DECAM to look for shock breakout, which was very fast-lived event. And we had 2-hour cadence during 1 week. And with this cadence, we were able to answer some question. But I mean, you needed to change the strategy of the telescope. So I hope there is more space for surveys within LSST.
Okay, since a lot we have to move. Vamos a siguiente presentación. El siguiente orador es Marcio Meléndez. La presentación va sobre el James Webb, desde the James Webb Space Telescope, Commissioning and First Year of Operations.
Ok, perfecto. Hola, ¿cómo me oyen? Bien. Bueno, muchas gracias por estar aquí, por la invitación. Y quisiera agradecer, aunque de repente debería guardar un poco el agradecimiento, pero a los muchachos que han estado organizando aquí las presentaciones, porque realmente hace mucho tiempo que no venía a una reunión y no hay problemas con nada de eso. Muchas gracias. Los veo corriendo por ahí a los muchachos, a los chamos venezolanos. Y además estar contento aquí. Montevideo es una ciudad hermosa, se camina muy bien. Y esta es, si no lo sabían, la puerta más antigua de Uruguay, traída de Italia y fue hecha en 1480. Si quieren más información, le preguntan a Cecilia, que es experta en esa puerta. Voy a empezar a hablar un poco en español porque quiero hablar sobre la conclusión de la charla. Quiero decir cuáles son los resultados. Y después vamos a ver un poco entonces un poco más de los detalles. Lo que quiero decir ahorita, sin sonar un poco, claro, vengo de cierta manera representando el telescopio espacial James Webb. Es bueno estar aquí porque me doy cuenta que se me había olvidado que la gente hace astronomía en otras longitudes de onda. Entonces está bien ver otras cosas, pero vengo a hablar sobre el James Webb, que está en una excelente condición. En cuanto a su calidad óptica, el desempeño óptico del telescopio está mucho mejor que los requerimientos. Estamos el doble, estamos a la mitad de los requerimientos en cuanto al error del frente de onda del telescopio. Y en cuanto a la estabilidad del telescopio, estamos 7 veces mejor que lo que se requería para el telescopio. Entonces el telescopio está en una gran condición. Sin embargo, el takeaway, lo que quisiera dejar en esta charla es que el telescopio como tal y el desempeño óptico del telescopio hay que pensarlo casi como otro instrumento. ¿En qué sentido? En el sentido que es dinámico también. Entonces, es importante que cuando ustedes para sus trabajos de investigación, y he visto gente haciendo, por ejemplo, quieres sustraer el PSF de tus observaciones o estás haciendo análisis temporales de exoplanetas y quieres exactamente tener una precisión perfecta de cómo es la función de dispersión del telescopio, tienes que poner atención en el momento en que fue observado porque hay variaciones muy pequeñas que para el 80% de las observaciones seguramente no importan, pero hay un caso que sí hay que importar. Pero no pasa nada porque tenemos todas las herramientas para ayudarlos a maximizar la cantidad de información que pueden sacar de las observaciones. En julio del año pasado, y ahorita apenas no hemos cumplido ni siquiera 2 años de funcionamiento del telescopio, en julio del año pasado fue bien bonito ver que todas las portadas, y digo todas las portadas, sabemos que no todas, pero vamos a decir que todo el mundo puso en sus portadas imágenes del James Webb. Nada más hermoso que ver esas imágenes del James Webb al principio del ciclo 1 de investigaciones. Fue muy emocionante, no nada más por ver las imágenes y por ver las capacidades que tiene el telescopio, sino también porque esto nos recuerda hace más de 30 años cuando vimos seguramente algo parecido con las imágenes que salieron del Hubble que estaban desenfocadas. Ahora, el mismos algoritmos para enfocar las imágenes del Hubble son los mismos algoritmos de recuperación de fase que se utilizaron con el James Webb. Y gracias a aprender en esas lecciones de misiones anteriores, nosotros no íbamos a tener ese problema y no lo tuvimos. Claro, siempre hay contingencias, pero nosotros aprendimos de esa experiencia y voy a hablar un poco más adelante sobre eso. Pero fue impresionante ver estas imágenes y todavía vemos algunas imágenes que salen por ahí y siempre son maravillosas. Esto salió hace unos días en la página del instituto. Por cierto, yo trabajo en el Instituto del Telescopio Espacial en Baltimore, que es el centro de operaciones del Telescopio Espacial James Webb, es el centro de archivos del Telescopio Espacial Hubble y va a ser el centro de operaciones de ciencia del Roman Telescope. Entonces, nosotros tenemos bastantes cosas pendientes en los próximos años y siempre, algo importante, quisiera que siempre nosotros tratamos de nutrirnos de mejorar los servicios que utilizamos o que proveemos en el instituto para ustedes, para la comunidad de astrónomos. Si ustedes tienen sugerencias, si ustedes tienen algunas cosas que quieran, que me quieran decir, me pueden enviar emails, podemos hablar al final de la charla, pero nosotros siempre estamos dispuestos a ver qué es lo que necesita la comunidad de astrónomos, en particular con el James Webb, que hemos tenido todos estos productos nuevos, los pipelines, las imágenes, estamos tratando de mejorar, de que podamos maximizar lo que es el retorno de la ciencia de todas las imágenes, que la gran mayoría ahorita están en los archivos públicos. Pero bueno, supuestamente, no sé si esto es un clickbait, pero dice que puso un récord de número de propuestas enviadas. Supuestamente creo que es el ciclo 6 de ALMA, que tuvo 100 propuestas menos. No sé cómo están contabilizados. Si ustedes piensan que estos números están equivocados, mándale un email al instituto. Pero lo que es definitivo de aquí, independientemente del número, es que ha habido bastante interés y este interés se ha aumentado con los años. Cada año aumenta el número de propuestas porque la gente ha empezado a darse cuenta de las capacidades que tiene el telescopio, pero también se ha vuelto un poco más familiar con las herramientas que tenemos para enviar propuestas, etc. All right, so my talk, I'm going to start a little bit with some of the introduction. I'm going to mention some of the optical telescope element commissioning. So this is the optical part of the telescope. Some of the images, some of the less popular images, but nonetheless very interesting images that may actually spark some ideas for you for the next cycles of proposal. All of the images that we collected during the commissioning process, not only for the OTE, for the optical telescope, but for the instruments are already available, publicly available on the MASS portal, on the portal for the Space Telescope Institute. I'll mention a little bit about the waveform sensing analysis and the first years of observation. But throughout the lecture, I'll be talking about a little bit about the lessons learned and how to. At the end, I have a slide where I can show you where you can get some libraries from PSF and some other tools that you can use for your science. So hopefully you'll have a good idea. This is not by any means the whole group, but this is a large group. After we did the multi-field alignment, basically, all the process of commissioning, we'll see later, happen at a single point on NIRCam, which is the instrument that have all the sensing capabilities. But after that, we're starting to move the secondary mirror to make sure that we have a good waveform error throughout the entire field of view of the instrument, of the telescope. Knowing in particular, and we'll see that all the instruments in the telescope, and this is thanks to Hubble, all the instruments in the telescope do have a focal mechanism. So they can adjust their focal mechanism independent of the OTE, except for MIRI. MIRI doesn't have a focus mechanism. So when we do these multi-field alignments, we're trying to give some weight to MIRI, especially to enhance things like coronagraphic observation, which we know are very sensitive to variations in the waveform error. Just a little bit about the telescope itself. I'm not going to spend much time on this. I just want to mention that because we launched on December 25th of 2021, it was a very special day because it's the birthday of someone that is very special, which is Isaac Newton. So we had a perfect, thanks to the European Agency of the European Space Agency, because the launch with Ariane 5 was perfect. So we have fuel for more than 20 years. Those are the predictions of the fuel. If you remember, cryo missions like Spitzer, Herschel, they're limited by the cooling they have inside, right, to keep their instruments cool. In this case, all the cooling is happening because of the huge sun shields that the telescope has that will cool down the temperature for all the instruments except for MIRI. And MIRI has its own cooling system that works mechanically. So, and it is closed. It's like having a huge fridge on space. So the limiting factor in terms of fuel is the fuel that is required to keep the telescope in L2 at its L2 position. And we have enough for 20 years. Now, that doesn't mean that the telescope will last 20 years. Hopefully it will last 20 years or more. There are many things that will degrade the quality of the telescope. And one of those things, and I'll talk about a little bit about that later, but you may ask questions for the 10 minutes. It's because in L2, if you can imagine a telescope that is 6.6 meters in diameter, it's completely wide open. It's not like Hubble that you have like inside a tube or anything. So you have something that is just there, it's just catching rocks. So at some point, we just have someone throw a rock at the telescope. And then I think that's going to be the main degradation of the telescope. It's going to be on the mirrors. And of course, the electronics of the telescope. You have cosmic rays hitting, but everything that is inside the telescope has redundant. So we have two NIRCams, we have two guiders, which are the instruments that we use to guide the telescope. And each of those have their own set of electronics that are also redundant. So we have a lot of things, but sadly, well, not sadly, that's nature, and that was the planning of the mission. We have a telescope in the middle of L2 that is just gonna, the mirrors are gonna get degrade over time. There is nothing we can do about that, at least not for this mission. And we are really moving, we're making very small adjustment. And when I say that the dynamic nature of the telescope, I really talk about very, very small things. Another lesson learned that we have from previous mission is that we did test the entire path of the entire optical path of the telescope several times. We did it at NASA Goddard during the 3 cryo testing missions, where we just put ISIM, which is the integrated science instrument module, inside a cryo chamber, and we shine line into it, and we just perform calibrations of the instrument. And then we connect the instruments to the mirrors, and we form something that was called OTIS, which is the OTE plus ISIM. And we put that inside this huge chamber that it was the one used, chamber 1 used in NASA Johnson Space Center, which is the one that it was used for the Apollo missions. I'm sitting here in the room where the Apollo mission is, and if you grab the phone, you'll hear Tom Hanks saying, Houston, we have a problem. I'm kidding, it doesn't happen, but it will be pretty cool if it happens. So, so it has a lot of history, and this is part of why we test this. That doesn't mean that Hubble didn't go through this process of testing, but because of the complexity of this mission, there were a lot of testing that happened, and we learned a lot, and that's why we also increase some of the requirements that we have for the mission. Not increase in terms of against the science cases, but give us enough space for us for the unknowns that could happen during the telescope, the functioning of the telescope. The process of commissioning itself, it wasn't that large. We started in February 2nd. Remember that when we launched the telescope, you have an idea where the mirrors of the telescope are, but because here we are in gravity, we have the gravity sag, we don't know exactly where the mirrors were. So the first time you point at the sky, instead of looking at a single target, you're looking at 18 copies of that target. And each of those mirrors have its own aberration. So it have their own deviation from the perfect models of the telescope. At the Institute, I was leading a group that is called the Shadow Team. We are the Wavefront team from the Space Telescope Science Institute, and we were performing all the phase retrieval and all the analysis of the commissioning of the images of the telescope, trying to align the telescope, right? We'll see the process of alignment in the next slide. Now, we need to mention that the commissioning of the optical telescope elements of the of James Webb, it was commissioned to Ball Aerospace. So Ball Aerospace was responsible to deliver a telescope with a good performance OTE. Now, after commissioning, then the Space Telescope Institute continued the trending and the analysis of the observation. So what we did during this time, it was we were shadowing, we were always repeating the same analysis that was happening with the Ball team, because every single step in commissioning had at least 2 different sets of results, meaning that two independent analyses for each step of commissioning, and we were looking for agreement every time we were going to move forward. In some cases, when we were trying to do the multi-field alignment, we have more than 2 sets of analyses to make sure that everything was correct before we move any of the mirrors, right? Every time we move a mirror, there was a chance for the mirror to get stuck or something. So every time we needed to move a mirror, we took it very seriously, and we really want to make sure that we have the best results in hand. But it was a very nice process. And quickly, maybe not much detail on the commissioning, but as I mentioned, we start with a random display of segments. And then the first thing that needs to happen is that first, you need to know where the segments are. So, so you point to a really bright star that is fairly isolated, and then you create this huge mosaic. Actually, it's the largest mosaic that has ever been observed with Webb. Was the first initial mosaic that we did for this observation, because in principle, we don't know what's the bull's eye of the telescope, right? So when you point to a star, if you're looking at that direction, maybe the telescope is looking into the other direction. So, but by luck, we were very close to the targets. We identify the segments, then you count the number of segments. We have 18 segments. Then you start moving the segments. You move those into an array, so you know exactly which one is which. Then you move the secondary mirror and start correcting for segment level aberrations for each of the segments. And then after you're done with that, you stack the segments, you start aligning until you have what is called a phase PSF. After you stock, you make everything coherent. So you have something that is phased. So we phase the telescope, and then we work with the multi-field variations across the focal plane of the telescope. And this is a very, very nice image of that final test of the telescope. This is after we did the fine phasing and some multi-field alignment. All the images that I'm showing you right now are all publicly available in the archives already. So you can go and look at this image and extract all this information, and I'll have programs ID for some of the images that I'm going to show you later. And this is one of our defocus images. So as I mentioned, NIRCam is the only instrument that has a sensing capability. So it does have a set of pupil wheels that have defocused the telescope. by certain numbers of waves of the focus. And because we're using phase retrieval with focus diversity phase retrieval, basically we maximize the fact that we know we can move in between the pupil and the image plane. We know the pupil of the telescope, it's the aperture of the telescope. We have the images, we can move, we can iterate between both, and we can reach a waveform map or a phase map for each of the observations. So that's basically the gist of phase retrieval. And that's why we have this set of defocus images. Otherwise, we could have defocus, again, the secondary mirror, but like I say, we move the secondary mirror very little at the end of commissioning, and we don't move the secondary mirror anymore because, so we use this set of lenses to defocus the images and do phase retrieval. You don't want to move the secondary mirror because then you'll change the quality of the PSF across the focal plane of the telescope. Here is a movie of the process of commissioning. I'm not going to show you the movie, but just to say that these are all real images. And like I said, we were moving, we identified the segment, we put it into this right configuration. And besides the phase retrieval that we did, we also did some coarse phasing where we're trying to find what's the piston values of the mirrors so we can compensate for the differences in height between the different mirrors. So now this is something interesting that not many of you have seen. This is the first light of the telescope. So this is the first image that was ever captured with James Webb. On the bottom of this, you see the observation, the actual image. This is NIRCam 3. This is a program that is called NIRCam 3, which is a functional test of NIRCam to make sure that everything worked as intended. So this is an actual image, and this was our observations. For the previous years before commissioning, we did more than 2-3 years of only practices where we practiced the entire process of commissioning doing very accurate simulations. So this is the first image of NIRCam, and we point the telescope to the LMC because we knew that for the first light, you want to make sure that you capture some light. So you point the telescope to something that we knew we were going to find something, even if the bullseye was a little bit off. This is another image that you haven't seen that often. We know about the science instruments of the telescope, but we also know about the FGS. FGS is the fine guide sensor of the telescope, is the one that we use to point the telescope. However, that can also be used as a science instrument, not for the astronomical community, in saying that it has the capabilities to be used as a science instrument. During some of the thermal slew testing that we have, we were collecting images with FGS. So this is an actual image of the FGS that when you stack all the images for the entire duration of our program, we're talking about 32 hours of exposure. Remember that FGS, because it's a guiding instrument, it doesn't have any filters, so it's a broadband. So maybe the capabilities for science application may be a little bit limited, but nonetheless, there is something that you can get out of this. And I'll show you in a second another case for an FGS that people in the exoplanet community is using already. Another nice set of images. Again, this is when we face the telescope. You can have images like this, where you see the huge variety of galaxies. Like we noticed very early on that any image with James Webb was literally a deep field, the amount of quality. So in this image, actually, we only have our calibration image. There are only 3 or 4 objects that exist in catalogs in this image. Everything here that you see here is new. So it's very nice that each of these are basically deep fields. And this is our program. We take, after commissioning, we keep monitoring the performance of the OTU and the jitter of the telescope. Every couple of days, we take images and we analyze those images. Actually, we just took a pupil image of the telescope, a selfie of the telescope. And we use certain tools, and we provide these OPD maps to the entire community. So you can go to MAST. Besides images, you can also download the OPD map. So the OPDs are telling you the optical performance of the OT. So you can download those, and from those you can create a PSF using tools like WebPSF. I'm the lead and the project lead for WebPSF right now. So you can use WebPSF to model these OPDs. If you want to subtract the PSF from your observations, if you want to subtract or model to do astrometric calculations, good precision. So when you're modeling fitting So you have this option. And this is what I was mentioning about the dynamic nature of the OTE. This is the wavefront error. So basically a metric of how well the telescope, the optical part of the telescope is performing as a function of time. I'm starting early in commissioning, and this is very close to maybe like less than a month ago, a few weeks ago. And you see all these peaks. Don't get too scared about this peak. The requirement for the wavefront error for the mission was 150 nanometers of wavefront error. We are typically below 70 most of the time, but we have these things that we call tilt events. And these are unplanned movements of the mirrors. And this is just a process, a mechanism where the mirrors are releasing some thermal energy. And we have these, and these have decreased in magnitude and in frequency over time. We have a bunch at the beginning because this was, we're cooling down the telescope, right? So that's why you expect to see many of these events happening early on the mission. But as we progress through the mission, you see less of those effects and you see less variation. And in reality, even we have these conservative values of trying to keep the alignment of the telescope. And every so often we make corrections to the telescope to make sure that the wavefront error is below certain values. But in reality, it's like every change that you see here produces changes that are less than 1% on the circular energy fraction of the PSF. So it has very little effects on the PSF. But nonetheless, if you're trying to do a fitting, photometric calculations, or TSOs, these may be relevant to you. This is exactly the same, but sort of like giving you a histogram on, we spend most of the time with the wavefront errors that are below 70 nanometers. Remember that the requirement was 150 nanometers. And in reality, this happened because we just have a recent large event on the wings of the telescope. So the telescope do have modes of oscillation that we see so often. So we are starting to understand those and correlate those with things that are happening on the telescope in terms of configuration. What are the things that are triggering some of these thermal release of energy? Like I say, don't be scared. This won't affect your observations in most of the cases, in the vast majority of the cases. And in the ones that what it does, you have the access to the OPDs, the phase maps that I mentioned before. This is just a summary of what I mentioned basically before. We have a gray stable telescope. We also have every couple of days, we do have jitter observations. We do a line of sight testing. So we keep track of all the line of sight changes of the telescope because that's also part of the requirements of the mission. Especially if you're thinking about the next big segmented telescope in space, the Habitable World Observatory, you're gonna have to do much better than this in terms of jitter and stability to really capture some of the exoplanets that we're trying to observe, right? So this is a pathway also to understand many of the systematics that we have. You'll have this on the presentation online, but these are the set of libraries that you can use with different objects. These are semi-empirical libraries that you can use to do your PSF fitting and extract some science out of your observations. And this is the link for WebPSF. Everything is publicly available. And I just want to finish with this image that was released a couple of, maybe last week of this is near the galactic center. And besides, yes, it's a beautiful image. It looks very nice. But I want to show you one of the challenges that the web has, which is that's the same. This is, you saw the previous image. This is what the guider instrument sees on the sky. So guider is trying to find a guide star, a precise guide star. So you have the precise WCS coordinates in the sky. And when you look at that part of the sky, you see a crowded field. It's very difficult to really match the right star, guiding star with the observation. So these are challenges that we're still working on understanding how we can improve these. Part of the improvement can be through better catalogs of near the galactic center of the galaxy on any of these crowded fields, right? So, but I just want to show you something nice because for a couple of reasons. Why also? So you see the challenges that we have. But second, all these images are available in the archives. You can go look at your observations and look at the guided products, and you'll get all these products. And interestingly enough, you can ask me later, these A by A frames of guidance, this is when you are in the fine guide mode. This is what people in the TSO, in the exoplanet community, has also been using to see if tilt events are real features of the star, or these are true tilt events that you see because of the OT, right? Because if you look that if your star has, for instance, a couple of days ago, people were talking about the atmosphere of one of the stars, and you see a bump on the light curve. Right? Is that bump real, or is that a tilt event? If you don't see that bump here, that means that it was part of the star, because remember, the guide star have nothing to do with the target. It's an arbitrary guide star that the telescope finds while it's guiding. Everything else that you see here that match the observations are systematic from the telescope itself. Well, thank you so much. This is all I have, but I want to tell you that the telescope is in great condition, and we have all the tools to help you maximize your science.
Muchas gracias, Marcio. Antes de empezar con las preguntas, yo quería felicitarles y agradecerles por la fantástica máquina astronómica que nos han regalado. Para serte sincero, yo era extremadamente escéptico de que fuera a funcionar. Mover todas esas y alinear todas esas piezas en el espacio es algo increíble.
Yo también era escéptico de que iba a funcionar. Los primeros años yo empecé trabajando y tú lo ves y dices, wow, esta misión es complicada, pero sí se puede hacer. Y mientras más aprendes de la misión, dices, wow, esto es bien complicado, no sé si lo podemos hacer. Y al final, cuando era el lanzamiento, dices, wow, ojalá que todo salga bien.
Y cuando lo alinearon,
cuando salió, de hecho, el proceso de comisión de nosotros, teníamos más de 40 procedimientos escritos con contingencia. Y nosotros no utilizamos ninguna de las contingencias, nosotros hicimos todo en el tiempo récord de, o sea, parece fácil, pero la preparación que tuvimos y la suerte que tuvimos con el telescopio es, bueno, se ve en las imágenes.
Increíble. ¿Preguntas?
Yes, congratulations again. Fantastic work. Just two questions. You mentioned 20-year lifetime for the limited by the fuel. Is that because you're using the fuel also for attitude control, or is it only for orbit maintenance?
The fuel is mostly to keep the orbit of L2. And we do some momentum, some load, and some other things, but it's mostly to keep it on that stable position around the sun, right?
Okay. And then one thing that we have every now and then with Gaia is the moon partially eclipsing the sun. And that makes a rather large effect thermally. Is that something you have to worry about, or is the orbit such that you don't expect to have any eclipses?
No, I think where we are basically just in that line in between the sun, the moon, and we do have restrictions on where we're pointing the telescope and where are the things that we have. But in terms of the orbit, the biggest restriction that we have now is to avoid the micrometeorite sun for observations.
Okay, so you never get
no
eclipses of the sun by the moon, or okay.
¿Dónde?
So as far as I understand, Hubble has redundancy in the guidance. Does James Webb have redundancy in the guidance?
Can you repeat that again, sir?
Redundancy.
Yes.
In the guidance setup.
Yes.
Right? So like instrumentally.
Yes.
So Hubble has, I don't know, 3 sensors. How many does James
We have
Webb?
2 sensors, guided 1 and guided 2. So we have that redundancy. And we actually use both depending on what's the best position angle for the science, etc. So you'll find observations. If you look at which guided instrument was used for guiding throughout the entire cycle, you see that we go in between 1 and 2. So you just move in between what's the best for the science cases that you're studying in terms of position angle, and you just choose which one happened to capture the best and brightest guide star at that time.
Hola, muy buena charla. Una preguntita sobre cuando hablaste de las degradaciones que va a sufrir principalmente los espejos a lo largo de los años. ¿Qué tipo de degradación esperan? Si eso lo pueden compensar con los actuadores o de alguna manera, que me comentarás algo de eso.
Sí, cuando tenemos la principal degradación son los impactos de micrometeoritos en los espejos, ¿no? Y de esos impactos que tenemos, un porcentaje de ese impacto se puede corregir a través de movimientos de los espejos. Un porcentaje. Nosotros tenemos 6, 7 grados de libertad, podemos aumentar, por ejemplo, en muchos casos, simplemente con el radio de curvatura podemos compensar parte de los impactos que tenemos. Sin embargo, hay una parte que no se puede corregir, no importa lo que hagas, porque el espejo se rompió un pedacito. No hay nada que se pueda hacer con eso. Si tú ves hasta ahorita la distribución de impactos, por eso que nosotros tomamos muestras también de la pupila, del pupil of the telescope, de la apertura del telescopio, ese selfie. Si tú unes eso con los impactos que nosotros vemos en el frente de onda y la distribución que tenemos, puede ser que nosotros de aquí a unos 20 años podríamos tener una degradación total que no vamos a poder corregir de unos 20, 30 nanómetros de diferencia, lo cual igualito nos pone muy por debajo de los que son los requerimientos. Sin embargo, los meteoritos son probabilidades de distribución en cuanto a masas, velocidades, etc. Tuvimos muy mala suerte de que nosotros en mayo del año pasado tuvimos un golpe fuerte de un micrometeorito en uno de los espejos y eso nos levantó el error del frente de onda como unos 10, 20 nanómetros en general, porque para ese espejo en particular lo levantó mucho más, pero en general, cuando tú compensas con los 18 espejos, acuérdate que cualquier cosa que pase es 1 sobre 18 de lo que estás afectando en el espejo. Entonces lo afectó un poco. Sin embargo, las predicciones eran que un golpe como ese debería pasar cada 5 años. Y nos pasó un mes después de haber completado el alineamiento completo del telescopio. Todavía el telescopio es limitado por la difracción a 1 micrón. Pero en ese momento teníamos una calidad perfecta del telescopio. Y bueno, tuvimos ese golpe un mes y no hemos tenido más ninguno de ese tamaño desde ese momento, porque era parte de la distribución. Bueno, al final es una probabilidad y tuvimos mala suerte. Tenía que haber comprado un ticket de lotería a ver si me salía algo.
Tenemos tiempo para una pregunta más. Volato al fondo, Alberto.
Marcio, ¿podés comentar algo sobre la degradación de MIRI y el espectrógrafo, el imager y el espectrógrafo, las bandas más largas?
Sí, bueno, todavía hay investigaciones activas sobre la degradación del telescopio, de MIRI en particular, no solamente en cuanto al performance como tal, sino los elementos que tiene adentro, ¿no? Las ruedas, el calor que se está produciendo, etc. No sabría exactamente cuáles serían los últimos números de lo que se espera en la degradación, pero es algo que se está investigando ahorita activamente, para MIRI en particular.
O sea que no hay expectativas de cuánto va a cambiar eso sobre
No.
el tiempo y demás.
No por ahora.
Okay.
Pero sí es algo que estamos investigando en particular para MIRI y un poco es entender las fricciones que existen dentro de los mecanismos y cómo eso ha estado cambiando ahorita en el tiempo. Y bueno, al final está la degradación fuera de los espejos, la de los instrumentos en general, ¿no? Y cómo se ha afectado con el tiempo.
Pues muy bien, tenemos que terminar. Muchas gracias, Marcio.
Gracias.